At this stage, you should understand the concept of a tolerance zone, specifically shape tolerances. And now we're going to move on to the next level, which we have to understand something about the relationship between features before we can talk about these tolerance zones. And that's what we'll be covering today. First thing is we'll talk about the feature relationships and then how we'll deal with that using a datum. And then finally what a datum feature corresponds to in our design specification. Well, let's look at relationships. If we think about our part that we're trying to manufacture, we note that on that part there are certain features that have a relationship with other features. For instance, down here, there are a variety of relationships we could describe. First of all, let's say this is a cylindrical feature. We might say that it's related to this top surface here, in that it's perpendicular, the axis is perpendicular to that surface. Or we might say that it has some relationship to this other feature in terms of the distance between the two, the separation. And so what we need to do is control this relationship between the features if we're going to produce a part that is interchangeable and meets the design specifications. The relationship is going to be based on some type of position and or orientation. And note that it's a relative position. We need some coordinate system to be able to talk about position or orientation. And the geometry is going to help us describe this relationship. When we think about how specific it is, in other words, how definitive we want to be about that relationship, we're going to base it on the concept of degrees of freedom. And that has to do with translation and rotation. So if you recall, your degrees of freedom in an XYZ coordinate system tell us something about the strength of relationship. And for right now, sometimes you'll see this referred to as 12 degrees of freedom, but we are going to think of it as 6 degrees of freedom, in that I have 3 translations and 3 rotations. So we're not so concerned about the direction from the standpoint of describing the relationship. We're more concerned about the axes and what is able to rotate or translate. So here we have in the z direction 1 degree of freedom of translation, in the x 1 degree of freedom of translation, y same thing, and then we've got rotation about that axis. So if I've got some object here in a coordinate system and we want to restrict that, then we're going to have to restrict the degrees of freedom. Now, how does that relate to our design specification? Well, you can think of your manufacturing processes as creating a feature, and during that process, as you know, deviations occur. So we get variation in the translation, in other words, location of this part feature, the rotation with respect to some axis. And so we're seeing movement of the part feature with respect to something. And that movement, either translation and or rotation, is something that needs to be controlled. In order to do that, we're going to need some references to control it. So let's look at some simple ways to control that motion. The simplest way is to have some point-to-point relationship. Now, point-to-point is kind of like the Earth in orbit around the sun, right? So we have some distance here, and that distance is maintained. However, we have rotation capability, and that's in 3 dimensions, so we can kind of think of this as spherical, but it's constrained. So we can't move closer, we can't move farther away, so we're restricting translation, but clearly we can rotate. There's nothing to control that, and therefore our rotations are unconstrained. So with this point-to-point, the only thing we can do is really control how far we're moving away from another point. And clearly there's nothing directional here, so again, rotations would not be controlled. Now, what if I had a point at a distance from a line? How can I describe the specificity of that relationship? Well, if this was my reference and I've got this point some distance from that line, I can't move away from the line, but I could move up and down the line. So that allows at least 1 degree of freedom of translation that is not controlled. I can rotate about the line. So I have, again, if I move around the line in this direction, so I have 1 degree of freedom of rotation that is not constrained. Beyond that, everything else is constrained. So that means that I've got 2 degrees of freedom of translation that are constrained and 2 degrees of rotation because I can't rotate towards the line, right? That would invalidate this relationship between the point and the line. So I can't rotate in that direction, I can't rotate in this direction, but I can rotate around the line. So in this case, I have 4 degrees of freedom that are constrained, 2 degrees of freedom, as we've seen, that are still up in the air. So we want to have the correct specificity for a relationship if we are going to be able to reference a geometry, in this case a point, with respect to a line, or vice versa. What about the relationship between a point and a plane? How would we describe this? Well, similar to the point and the line, what we see here is I can translate in any direction in the plane. So those are 2 degrees of freedom, translation, that are not constrained, which means I have 1 degree of freedom of translation that is constrained, and clearly that would be the distance here. This is fixed, and so I can't translate in that direction. Therefore, 2 degrees of freedom are unconstrained. And then if I look at rotation, I can't rotate about the x, let's say this is the x and y axis here. I can't rotate about the x-axis, and I can't rotate about the y-axis. But I could spin, so to speak, around the z-axis if our orientation here is like this, and therefore we have 3 degrees of freedom that are constrained. 2 rotations and 1 translation in z. Clearly, if we need more specificity in a relationship, we're going to have to constrain more degrees of freedom. A completely specific relationship would be if we constrain all 6 degrees of freedom. Anything less than that allows for some movement, either rotation and or translation. So in many design specs, you're going to see 6 degrees of freedom in order to completely control that relationship. But there are instances where you don't need that many degrees of freedom, and then you'll see fewer constraints. So in order to do that constraint, to enforce that constraint, we use something called a datum. And a datum is a concept, and by a concept I mean it doesn't really exist. So this datum that we have is a description of some type of relationship. It will have some correspondence to a part feature, but the datum itself is purely a concept, which means we have a theoretical reference. However, when we make the part feature, it's not theoretical, it's actual, so that means we have to derive this theoretical reference from that part feature. If I look at location or orientation of some feature, I can think of it as we just did in those 3 examples with respect to a datum. In other words, the specificity of that relationship in terms of degrees of freedom will be determined by how many datums we're going to use in this relationship. The actual location and orientation of the feature will deviate from nominal. So when we make this part feature, it will move, translate, and or rotate by a very small amount, hopefully, and that will be a deviation from the nominal specification. From a design perspective, the designer is trying to define important relationships. So not every feature on our part is going to have a relationship to one or more datums, but there are important relationships that must be maintained. Otherwise, we're going to have problems in terms of fit and function. From a manufacturing perspective, why is this important to us? Well, what we're going to see is in our processes, we're going to have to locate our parts on workstations and typically in a fixture or jig. And when we do that, that will be the basis for locating those parts. It will also affect the sequence in which we perform operations on those parts. And you can think about that in terms of your references. You need those references prior to actually creating the part features, and we'll talk about that when we get to our processes. Well, life is pretty simple for our datum geometries. By datum geometries, I mean what are these theoretical geometries that we're going to use to describe our references. And you only have three choices. So it will come down to whether or not you're dealing with a point as a datum, or a line, or a plane. Those are the only three choices. So don't ever tell me it's a circle or a box or some other geometry. These are the only choices that you have. And that means we have a point in space, some line in space, or a plane. These will somehow be derived from part features. And the way we do that is we abstract them from datum features. So we need to find the datum features in our design spec and know where our point, line, and planes are. Because again, these are theoretical, and we're going to have to use them when we do things like inspection or setup of our parts and other types of operations. What is a datum feature? Well, we're going to take some surface geometry derived from a part feature of some kind. And from that surface geometry, we're going to abstract that into a datum. So the actual surface that we're looking at is going to be used to locate fixture part during a process. And that surface is going to be our datum feature. We abstract that and create a datum. Now, what are the three possibilities? Again, don't forget, point, line, or plane. There are no other possibilities. So somehow we have to go from a surface to a point, line, or plane. So when you're looking at the design spec, this is what you should be thinking about. What surfaces are we dealing with, and how do they correspond to a point, line, or plane? So here's a very simple example. We have a cylindrical part feature, and that part feature, we're going to use a cylindrical wall here, and that cylindrical wall is the surface of interest. That's our datum feature. From that, we can abstract a line, right? So you really only have three choices here if this is the part feature corresponding to the datum, right? If I've got a cylinder, I could only have a point, line, or plane. Well, think about when you abstract these point, lines, or planes, think about a locating principle. In other words, how would I locate this datum in space? The only way to do that is to have an axis, right? And that tells us where the cylinder is. And therefore, this axis corresponds to our datum. So we take our datum feature, we abstract it, and now I know I've got a line that I can use as a reference, and it corresponds to our part feature, which is cylindrical. Well, when we actually determine this datum, because it is theoretical, what we're going to do is estimate it. And in order to estimate it, we need an actual part, right? So we're going to manufacture the part and then take a bunch of measurements to estimate the location and orientation of that datum. Each estimate deviates from the nominal. So it's imperfect, right? In other words, there is the potential for error here. And keep that in the back of your mind. What contributes to errors in manufacturing? This is going to be one of them. So we'll introduce errors into subsequent processes because we have estimated this datum. It's imperfect. So when you're thinking about datums in your design spec, you should be thinking about these kinds of questions. The primary one is you have to be able to identify the part feature that corresponds to that datum. So there's a specific part feature. And what elements of that feature are necessary to determine the datum? So you're thinking about the surfaces, and that surface corresponds to our datum feature. If you understand the datum feature, then what is the geometry that corresponds to that datum feature? The other thing you should do when you're reviewing a design is think about what would make a good datum from a manufacturing point of view. Typically, and this is not always the case because there are constraints, there will be dominant features in a design. And by dominant features, we mean major features, right? So if I've got a hub of some kind, it may be the inner wall of that or outer wall, again, a major feature in that design. And if it's going to be a good datum in terms of being usable, first of all, it has to be accessible. Otherwise, it's going to be difficult to estimate that datum. It will need some surface area. If not, then it will be difficult to determine exactly where it is. And it shouldn't be flexible, because if I've got flexibility, that means I'm going to have a lot more error in estimating that datum. In terms of our manufacturing processes, hopefully we expect very small deviations in that datum surface. So at this point, you should understand the notion that as a result of our processes, we have the potential for translation and or rotation of part features due to deviations in our result. And we're going to describe our relationship in terms of datums and try to constrain how much that part feature can rotate or translate. In order to find the datum, you need to locate the datum feature, and from that derive the theoretical geometry for that datum. Don't forget, it's theoretical. It doesn't exist. It only exists in your mind, and therefore you have to find it by using various surfaces on your part feature. A datum can be a point, line, or plane. Those are your only choices. One or more datums are going to be used to make this a very specific relationship between a part feature and a set of datums. And the datum will be extracted from that part feature surface. So, how do you know you have a datum when you look at a design specification? Well, you need to be able to identify the datum. And so, we'll be looking for what we call a datum feature symbol. And in that symbol, there will be a datum identifier. That datum identifier will tell us what datum corresponds to that datum feature. And then from that, we'll identify the datum geometry. What is the datum feature symbol? Well, what you're going to see is a datum attached in a variety of ways to the design spec. And here I've got three simple examples. What you're looking for primarily is a box. And as you can see here, that box is our datum symbol. And we have a variety of ways in which it will appear. Within that box, you're going to see the datum identifier, which is an uppercase letter. Typically, you're not going to see anything above an F, so we usually begin at A, B, C, D, and so forth. It would be rare to see a letter above F, but it could happen. What we're trying to do is indicate the part feature that corresponds to the datum using this symbol. And the way that is done is we somehow attach it to the surface, or we have a leader pointing to the surface, or it's attached to a feature control frame. So the simplest form is to take the box with the datum identifier in it, attach it to a surface using a closed or open triangle. And you'll see it in two forms. This is the preferred form here, but you'll also see it attached with an open triangle, and that goes along with previous versions of the specification. So in older versions, you may see that open triangle. Here we see it attached to a leader line. So for B, we are pointing to this surface, and there may be dimensional tolerances here on above this leader line. We've already seen a feature control frame. Here we have circularity, and what we're saying by attaching this datum symbol to that is that the feature that we're controlling in terms of circularity is also a datum, and this is quite common. So don't confuse this A here with the feature control frame. I know that's often the case. Students think that somehow this A is part of this feature control frame. It's independent of that. All we're saying is the feature that we're controlling with circularity is also a datum. So your first step is find the datum feature symbol. What are they? And those are fairly easy to identify. And then the next step may be a little more difficult, but with practice I think you'll see it's not too bad. What you'll do is determine the geometry for the datum features based upon what this feature symbol is attached to. And then from that datum feature, try to identify the datum geometry. So here's a simple example. It's easy to see you have two datums. The question is, what is datum A and what is datum B? That's the ultimate question, right? So A corresponds to what? And B corresponds to what? Well, our first step is find the surface based on the datum feature that corresponds to A and B. If I look at A, again I've got a 2D drawing here, A is corresponding to this side of the part. So you might leap to the conclusion, well, A must be a line because it's attached to that line. But it's actually attached to that surface. And that surface is going to be the side of this part, which would correspond to a plane. And then when I look at B, I note that I've got this circular arc here that I'm attached to. So the question is, what is the surface? And the surface in this case would be a half cylinder. So we're looking at a cylindrical surface, and if we're dealing with the cylindrical surface, we have to reduce that somehow to a point line or plane. And going back to our previous example, the only thing it could correspond to would be the axis of this half cylinder. And therefore, we would say B is a line. In our second example here, we have three datums, and these datums are attached to surfaces. So you should recognize at this point that A is attached to this surface, and therefore A would have to be a plane. B is attached to this surface, and therefore B would be a plane. And finally C is attached to this surface, so C is also a plane. So we have three planes in this design specification. In our next example, clearly we have two datums, A, B. Note that B is attached to this leader, and you can also look at the information here because that will give you a slight hint there. We have a diameter symbol, which means we're talking about this outer wall of our part, and it has a diameter in that range. What we're also saying is that that feature corresponds to datum B. And therefore, datum B is a cylinder. And as we've seen before, the datum corresponding to a cylinder is going to be a line. And that line would be the axis going down the center line for this outside wall. And then A is on the top surface here. If you note, A corresponds to this datum feature, which is a 2D annulus. So the question is, what datum, point line or plane, would correspond to that 2D annulus? Well, I have a flat surface, therefore I'm going to abstract that into a plane. Now you might be tempted with this 2D annulus to treat it as a circle and therefore say that the center point is the datum corresponding to that 2D annulus. But again, you have to look at it as the surface itself and not, for instance, this inner circle and this outer circle, but I'm looking at the surface itself. So don't be tempted to use the edges there, but use the surface. And we end up with a line and a plane in this example. Example 4, that's pretty straightforward. We have an example of a feature control frame. And if you look at the feature that's being controlled, we're talking about a half cylindrical slot corresponding to this surface. And we're constraining it in terms of cylindricity. And then we note that datum A is also attached to that feature. Well, at this stage, you should recognize that I've got a cylindrical datum feature, and therefore we're dealing with the axis of that feature. So datum A is going to be a line. Now there are some nuances that you should pay close attention to. And one of them has to do with where is the datum symbol attached. So here are two examples where we end up with a different datum depending upon the attachment point. The one on the left, we see our attachment is at the dimension line. If you see that, then what you're really saying is this is going to be treated as a feature of size. And you'll see that term used in other instances as well as we go through the semester. If I have a feature of size here, then what we're really talking about is the midplane between these two surfaces. And so we have this theoretical midplane that locates this feature of size. And it could be a slot feature in this case, or a protrusion of some kind, but we're locating it using the midplane instead of one of these surfaces. Versus on the right here, note the attachment point is on the dimension line, but is on the extension line, not the dimension line. So if it deviates from that dimension line, then we're talking about an extension line of this surface here, which means your datum is this plane on this side. So just by moving the attachment point, we see we can have a completely different datum, and you need to pay close attention to that, especially when you have a dimension line and a datum feature symbol near to it. Okay, the other slightly complicated datum has to do with a pattern. So when you see a pattern of features, think of the datum as referring to the centroid of those features. And the centroid is based on constructing a polygon. So in this case, C, and I'll let you determine on your own what B and A correspond to. At this point, you should be able to determine that. We have a pattern, and I know it's a pattern because of this 4 times here, which means I've got 4 holes in that pattern. And C is going to correspond to that pattern. So what do we mean by that? Well, we're going to construct, essentially, from the polygon, we can construct 2 planes that intersect at the center of that pattern. And therefore, we're dealing with an axis which would correspond to a line for C. Well, we know that B is a line, and you should readily see that. And the question is datum C equivalent to datum B? And think about this when you actually make the part. Will datum B be the same as datum C? The answer is no. Now on the design, they look exactly the same. That the axis for B, the axis for C, would be in the same location. However, when you make this part, there will be some deviation, as we've already said, due to the degrees of freedom. And so B and C will not be in the exact same location, and they will not have the same orientation. So we come away with the conclusion that C is not equal to B. Now we could try to control the relationship between C and B, but they're not equivalent. Okay, so when we think about defining this relationship, it's really the degree to which we're going to control it. And that has to do with first of all, the dimensionality of the datum, as we've seen in previous examples in restricting degrees of freedom, and how many datums we'll use to describe the relationship. We've already seen that a point can restrict up to 3 degrees of freedom, a line 4 degrees of freedom, and a plane 3 degrees of freedom. By themselves, those datums cannot restrict all 6 degrees of freedom. So if I have a point, how am I going to restrict the other 3 degrees of freedom? If I have a line, how will I restrict the other 2 degrees of freedom? And the same thing with a plane. Well, we need to combine them together. So at this point, you should be able to recognize when you have a datum feature symbol. And that datum feature symbol is the box within which we identify the datum using a datum identifier. So when you think datum feature symbol, I've got a box, and then within that, my datum identifier, A, B, C, D, and so forth. And then the datum geometry, corresponding to our point, line, or plane. What is the effect of that datum geometry in terms of constraining the specificity of the relationship? That goes back to our degrees of freedom that we discussed previously. So a datum is always referred to by an uppercase letter, and our datum feature symbol is attached to a feature. So you need to identify that feature. That's critical. If you're going off of the wrong feature, you're going to make a lot of mistakes. So make sure you have the right feature, and from that feature, you will determine the datum geometry using one or more surfaces. Don't forget the nuance. If we're attached to a dimension line, that's going to refer to a completely different datum than if we are just attached to the extension line. So now that we know about datums, the next stage is how do we put the datums together and use them to describe our relationship.